my name's Lauren. I am a PhD student in Chris's group, which is, as he said, the Natural Materials group, and I'm here to talk to you about gastropod mucus and how we look at it using optical profilometry. So just a quick overview. What is gastropod locomotion? So you've got a little bit of context. This is a snail and a slug moving, and gastropods use a very unique form of locomotion called adhesive locomotion, and this allows them to go over a vast range of substrates and also in a lot of directions and angles, which is why we're interested, because it's useful as an adhesive and a lubricant. And there are two key components, the first being pedal waves, which is the muscular movement, and you can see this underneath the garden snail at the top. And the second is a thin layer of mucus that they travel on top of, and that is what we're interested in as a material scientist. So how thin is this mucus layer? Well, what we found is Denny back in the 1980s measured the mucus thickness in Ariomax columbianus, which is the banana slug, and he did this by fixing the animal and the attached mucus. And this got a value of 10 to 20 microns thick. But this assumes a consistent thickness. Then in the early 2000s, Davies looked at the rehydrated mucus in this marine gastropod, which is Dilitterina litorea, by using focal distance. And this showed it to be 5 to 50 microns thick, but most interestingly, that it had a convex profile and it was not consistent. So why do we care about this mucus thickness? Why am I interested? Well, the thing is, it helps us bridge the gap between the native state of mucus and experimental research, which is really important when we're designing experiments. It helps to link the material properties back to animal behaviour, and it gives us an insight into the true cost of locomotion for these animals. So our species, we looked at 3 terrestrial slug species. We've got Ryan vulgaris, Ryan flagellus, and Limax maximus. Did a total of 27 gastropod trails, so this is 3 specimens for each species and then 3 runs for each specimen. And these species represent 2 separate families within slugs. We've got the Aranidae family and the Limaxidae family. Only one from that one though. But yeah, how do we explore this trail structure? So what actually do I require from my methods? Well, the first thing was we didn't want to disrupt the native mucus trail. This is something that often happens with things like FTIR and stuff. If you need enough material, particularly rheology as well, involves scraping the mucus up and disturbing it. We wanted an overview of the whole trail. Again, a lot of things only look at a tiny section of it. So we looked at FTIR, but you're only looking at maybe like 2 millimeters, if that, which isn't how big a slug is. And then we wanted to observe the gastropod behaviour. The first 2 we could do using optical profilometry and microscopy, and the second one we did using video analysis, so we always record our slugs whenever we're doing an experiment. So with the microscopy, this gives us good context. You can see that there's sort of artifacts and some sort of thicker mucus on the side. We've got some alignment and it looks slightly thinner in the middle. But as we move back to the other edge, there's sort of, well, you'll see in a second, some areas of interest again, like just here. And now this gives us a good understanding of what the trail looks like, but it doesn't really tell us how thick it is or how we can attune our experiments to it. So for that, we used optical profilometry. It will change, I hope. There we go. So how does that work? This is a technique that is non-contact, which is really, really good. And what you do is you put some white light into a beam splitter. This bounces off a reference mirror and onto your mucus, or whatever material you're wanting to look at, which then all goes back up into a camera. we get a interference image, which then can be processed using the software and computer to give us a 3D reconstruction. And that's what I work with to look at the mucus trail section. And now this is a bit wonky because of the fact that it's a large stitching area and you have a tip and tilt to get the interference image properly aligned. And so I fixed this by giving anchor points either side of the glass, because I knew the glass was flat. And then I could flatten this out using a baseline to give me my mucus trail. And we did this every 2 millimeters up the trail to give you a sort of overall topography for each trail. And so for every single trail, we then average these to give us our average trail topography per run. So as you can see here, and we did it in 10% divisions across the width of the trail so that we can then compare between different animal thicknesses as well. So the first thing I noticed was that this is very similar to what we found in Davy's work. And actually, we do get some of that variation as well, as you can see in the sort of lower values. But the thing that was most interesting, in quite a few of our trails, we had the complete opposite profile. So we moved from being sort of a concave profile to, no, convex into concave. I never get those two right around. So what is impacting this mucus topography? And the first thing we looked at was the animal speed. Now this is one specimen for each species, and this is all 3 of their runs. And I'll zoom in a little bit because it's a bit hard to see from a distance. But you can see that for the, let's see if this works. Yeah. For the species over here, this is the one that is all quite slow. It has all of that convex profile. But then as we look at the other 2 species, where they're a little bit faster, so up in sort of 11 and 10, this is an arbitrary unit of just normalized to the average of the speed of all runs. You can see that the mucus sort of inverts that topography, and we think this is probably due to the animal shearing the mucus as it's moving alongside it, and it's changing the shape of their topography. So this gives us a good insight into how they're manipulating the material to move it back into a lubricant state, and what we can then do when we want to make it into an adhesive ourselves. So we looked at topography, but what impacts thickness? The first thing we thought was probably specimen mass. Makes sense. The larger the slug, the more mucus they need. And well, no. Not really. When we had a look at it, we realised that it's sort of completely random. There doesn't seem to be any connection to the size of the animal. They're sort of producing a sort of relatively consistent but kind of random rate. So the next thing we went back to was, what about speed? Speed impacted topography, so does it impact thickness? And the answer to that is maybe. We're not 100% sure, but what we did find is that the Aranidae family had a much lower range of speed, but had a vast range of thickness compared to the Mercedidae family, and that is probably due to the animal's behaviour. So the Orion slugs, those are detritivores. They are completely non-predatory. They are sort of herbivores. They'll eat whatever's on the ground. They don't need to move that fast. Whereas the Limax maximus is an omnivorous slug. It typically prefers its mushrooms and sort of leaves, but it is an opportunistic hunter, so it does need to speed up. But this leads us into a state where we're like, is there a sort of maximum rate of production that these animals can have? So the faster you go, the less amount of mucus is deposited. So that's something we're looking into now. So when we looked back at what the mucus thickness was, you can see here that what's quite interesting across all the runs, it's fairly consistent across all the animals. We're sort of operating within quite a sort of small area. But what we also found is this is much thinner than expected compared to both Davy's and Denny's values. Now this might be because we were looking at dried mucus instead of hydrated mucus. A mucus is 98% water, so I sort of did a sort of percentage increase to see what that would look like. And you can see that this is getting a bit closer to their values, but is still substantially lower than that. But this might be due to the fact that we have volume expansion ratios, and those are very sort of minimally understood when it comes to gastropod mucus. But the main thing is what about the hydrated mucus? Because we were looking at drying, what is it counting for that massive gap between the two? And we've started to do a preliminary study, and this is what I'm looking at next, using optical coherence tomography, which we can use to visualize the wet mucus under the slug as it's producing it. And we did this using our species Nemex maximus on a sort of test run. And I've got a little video here. You can see that is the slug. As it's moving, it's depositing its mucus behind it. And that is the mucus in its hydrated state before it dries out, which is very quick. Sort of, we're talking a couple of seconds to a minute max, which makes doing experiments an absolute nightmare. But what we found was that it appears to be about 30 microns thick, so sort of a lot closer to the values that Denny and Davies were getting, but more importantly, it was actually quite a bit higher than the values that Denny was getting initially. So what does this all mean for the animal's cost of movement and the actual, output for the animal? Well, Denny estimated the cost of locomotion of gastropods ages ago using his model species, the banana slug. But the problem with that is slugs don't move at a regular speed. To do cost of locomotion, you have to have an animal move at a fixed metabolic rate, which is a fixed sort of movement speed for over a meter. And slugs, I'm sure they can do it, but they won't do it on command. It's the main thing to know. So all of this is sort of taken a little bit with a pinch of salt. Again, not something you should say when you come to slugs, but there you go. And using this mucus thickness, Denny estimated that mucus production is the largest component of cost for adhesive locomotion. But what does the difference in the hydrated mucus thickness versus the dry mucus thickness mean for this cost of adhesive locomotion? Well, dry mucus thickness appears to be relatively consistent no matter what the species are, even though there's a lot of variation in the profile for its hydrated form. There is much higher variation when it's rehydrated and in its native hydrated state. And the mucus components, it might just mean that we need to start considering them a little bit more like a composite. So we've got our dried thing, a bit like a sort of insoluble solution. We've got our dried components, which would be our active things like proteins, glycoproteins, all of that. And then we have our water, which makes up most of what mucus is, which is very interesting for when we are trying to design our biomimetic materials based on this, is understanding that link between our sort of solid state stuff and our liquid state. And this means that for animal behavior, environment will have a much greater impact on hydration costs in adhesive locomotion, which makes sense. Slugs don't like going out in arid conditions. They like it to be rainy and wet, and they want to be in an environment where they are not having to use their own moisture to fuel their own mucus production. So in conclusion, optical profilometry is useful in allowing us to visualize the native topography of gastropod mucus. We can begin to connect trail traits back to the animal behavior using video analysis and then using that to inform our biomimetic designs. And our active components in mucus are relatively consistent, but mucus hydration appears to be an unpredictable cost in adhesive locomotion. Thank you very much for listening. If you've got any questions, please let me know. Thank you to the funding from EPSRC, the Bio Ladies for having me at this event, and then Rui Hearn, Elle Hudson for helping with the data, and my supervisor, Professor Chris Holt.